Alright, good morning everyone. We'll be starting class in 1 minute's time. Alright, morning everyone. Today's lectures are going to be basically a review of our signals and systems knowledge from UCNG 2011. And whereas we're not going to be doing like a full review of the entire course, we're just going to be doing a review of what's going to be applicable towards this course, DSP. And the material covered in these two lectures that we're doing today are going to form the basis of material that we're going to be covering throughout this entire course. So if you have any questions regarding anything during the delivery of these lectures, please feel free to interrupt and ask your questions in the chat, and I'll answer them accordingly as of such. So let's get started. So the general overview of what we're going to be doing today is that we need to review our signals here with respect to continuous, discrete, and digital signals, as well as our systems with respect to continuous and discrete systems as well. We're also going to be looking at the periodicity property, which is going to play a very important aspect throughout this lecture, and the unit step, which is basically our basic signal that we tend to deal with for any sort of signal analysis regarding some sort of systems as well. So, as we know from our signals and systems course, if we have a general time domain signal here represented by our steel pen note, giving us a nice sinusoid, if we convert this into the frequency domain using the associated Fourier transform, we'll obtain the spectrum of the signal where this peak here represents the maximum magnitude of the entire signal here from the time domain, and that x-axis here represents the frequency of this entire wave itself. We also know that in transforming a wave from the time domain into the frequency domain, it makes doing certain types of working and processing a lot more easier in order to analyze characteristics of the signal. So, and then even after we do all those processing and manipulation of the signal in the frequency domain, we can then do the inverse Fourier transform to get it back into the time domain. But like I said, because we're just doing a review here, and we know that the continuous time Fourier transform uses a lot of complex integrals and so forth and whatnot, we're not going to be doing that throughout the entire course. For this particular course, we're going to be looking at a more effective method when we watch it in the discrete time series, and it's a lot easier to do when we get on to those lectures in particular. Now, because this course focuses more on discretized time signals, that's what we're going to be doing more work on throughout the entire course itself. So, if we had a general sequence here, which we can see here, it's 0 for everything before 0 and everything after 10, and 1 for everything in between. We can still do our standard signal manipulation tactics that we saw for our continuous time signals and signals and systems. So it's possible for us to delay our signal accordingly here, to invert it, and then we can just make our unit step sequence as such. However, when we do write these signals, we're going to be using square brackets instead of curly brackets. So if we have our input sequence here being x of n, if we delay this such that instead of it start at 0, it starts like at about 6 here. I think it's 6? No, it's at 4 here instead, sorry. So instead of it starting at 0, it's going to be started at positive 4. The delay here is represented by n minus 4. Similarly, if we wanted to invert our x of n sequence here, we just say this is going to be a minus x of n. And a unit step sequence, instead of it being u of t, which we know for continuous time, is just going to be u of n instead. So the reason why we use the n index here is because in discretized time, the periodic time, which represents our sampling time, is going to be capital T, which intends to be a constant value. And the n index here represents the instance at which that sample occurs. So I'm just going to write this here on the slide. T here is our sampling time, which tends to be constant. And then n here is the index for a particular sample. And then visually, what this means is that if we take this sample here and this sample here, and we measure the time between those two samples, that would give us t. And n, represented our index here, is going to be on our x-axis. Our y-axis, as normal, represents the magnitude. So for instance, if we say we wanted to know, okay, what's going to be the index of this particular sample here, we see here, okay, on the x-axis here, it's going to be at 0, 1, 2, 3, and then here it's going to be 4. So this here is going to be x of 4. Similarly, if we said we wanted the index of this sample here, we see here this is before 10, so that's going to be 9. So that's going to be minus x of 9. Because this inverted sequence here was minus x of n. But remember, because we're dealing with discretized time signals, the periodic time or the sampler time, capital T, remains constant because it's going to be the time taken to take successive samples. So if you take any two successive samples, meaning two samples next to each other, and then you just watch the time between them, that's going to give us our capital T being our sampling time or periodic time throughout the entire discretized time series. The n part is going to be our index for a particular sample. So n here now represents our x-axis values regarding these discretized time plots accordingly. You'll have to excuse me if a little bit, my throat's giving me a bit of trouble this morning. Alright, so because we deal with discretized time signals, that means instead of being x of t, which we know conventionally, to be our continuous time representation, so x of t here was for continuous time. X of n here represents discrete time. So if we're delaying a signal accordingly, that means if it's a delay, it's going to be x of n minus k. And if it's an advance, it will end up being x of n plus k, which is similar to the advance and delays that we saw for continuous time signals. If the signal is reversed, being that it's flipped horizontally, that means it's going to be x of minus n. If it's inverted, meaning that it's flipped vertically, it's going to be minus x of n itself. And traditionally, the unit step means that for everything n before 0, it's going to be 0. And then for everything n greater than and equal to 0, it's going to be 1, as we saw in the previous slide. And this normally is denoted by u of t for continuous time, but because we deal with discretized time, this is going to be u of n instead. So remember, everything in the discretized time domain is respect to n, and it uses square brackets in particular. So if we wish to generate a discretized time signal, this comes like if we just say, okay, let's represent our vector of n values here, spaced by 1 space and apart. So this is going to be from minus 20 to 20, positive 20, and it's going to go in spaces of 1. So that's going to be minus 20, minus 19, minus 18, and so forth, going all the way down to 20. And then we just factor in that n vector here for our x signal, which is going to be our graphical signal that we observe here as of such, giving us our nice cosine wave representing our samples. Similarly, if we do this for some sort of exponent decaying wave as well, the same effect has occurred, where we can see that the samples here are represented accordingly as of such, where the x-axis here gives us n, and the y-axis here basically gives us the magnitude of our x signal accordingly. Now, in dealing with signals in particular, to make our life easy, it's important that we understand that if we can figure out if a signal sequence is odd or even. So an odd sequence here is when if you can take your general x of n signal and you can invert it and flip it accordingly, invert and reverse, sorry, and you get back the same sequence as such. So what this means here, if we watch our x of n signal here, which is as is, and then we flip it vertically, so mean that we invert it, and then after we invert it, we reverse it, and if we get back the same sequence, when I say reverse here, I mean that we're flipping it horizontally, and if we get back the same sequence, we basically say that this signal here exhibits odd properties. Similarly, for an even sequence, all we need to do is just we need to reverse it or flip it horizontally. And as of such, once you obtain back the original sequence for this reversal of the signal, that means here is that the signal exhibits even properties. So one thing to remember, because I'm getting this question here, is that this x-axis here is respect to n, not t. Remember, t here is our sampling time. And this is basically going to be constant. So when we see a signal here being like x of n, in reality what this is x of n capital T, where the capital T here is constant, because T there could take any value that represents our periodic time or sampling time. N being the index at which these samples occur is represented on the x-axis here. So this here is going to be sample 0, this here is sample 2, this here is sample 4, this here is sample 6, and so forth. And T there basically just gives us an idea, okay, let's say if we wanted to convert back this signal from discretized time to periodic time, we need that capital T here being the sampling time to figure out, okay, what's going to be the frequency of our signal to get it back into continuous time. Because we deal with discretized time, we don't really focus more on the frequency, we focus more on the sample indexes being n itself. So this t here between two successive signals, two successive samples, that can take any value. The purpose of t is just to reconstruct the signal back into continuous time to give it the continuous frequency as represented. That's one key thing to note in particular. Discretized time, it goes on the x-axis with respect to samples. So it's going to be sample 0, sample 1, sample 2, sample 3, and so forth. In continuous time, remember the x-axis with respect to t, so that's going to be instances of time. So t equals 1 second, t equals 2 seconds, and so forth. That's the key difference between continuous time and discretized time signals. Continuous time being respect to time, discretized time is going to be respect to the sample number. So this slide here just basically recaps what I just said about odd and even sequences. So an odd sequence is when you invert and reverse the signal and you get back the same signal. And an even sequence is going to be when you just reverse the signal accordingly and you get back the same signal as well. Even when, let's say, you have some sort of weird signal and you can't exhibit the entire thing having even or odd properties as of such, you can break up the signal into individual parts of the signal itself, and if those parts can exhibit even and odd tendencies, you can then perform processing on those parts independently and then combine the results of the processing to get back to the output signal as of such. And that's an advantage that you can do here when you're using discretized time signals, because numerically what it is just basically a sequence vector of magnitude values. So that's a huge advantage when you're dealing with discretized time signals. It's a lot easier to break up your signals and treat them as independent slots. And then after, when you treat each independent signal, sub-signal, as you process each part, you can then combine back the results accordingly and you'll get back the entire result as is. So one thing to also note is that, let's say if we had a periodic continuous time signal here, we know here that if we try to represent this in a discretized time, we'll get our stem plots here only showing each sample as of such. But in the instance where we tend to have the samples not lining up properly with the signal, we tend to have something we refer to as a sort of break effect that we can see here accordingly in between these two samples if the signal is repeating itself. So instead of having like a nice flowing line, as you can see here for continuous time, because we have basically the instantaneous sample values taken, typically when you do discretized time, sometimes you lose the general shape of the graph. And this will depend on how many samples you take from your continuous time signal. So the more samples you take of your continuous time signal to represent it in discretized time, you have higher accuracy, yes, but you use more memory, because that means you need to take more samples. And as of such, because you're using more memory, if you have to do any processing, it's also going to take a longer time to do the processing because there's more samples. Conversely, if you take less samples, yes, you're going to have less memory, so any sort of processing is going to be faster. But because you took less samples, the end result is going to be less accurate. So there's a trade-off that you need to consider when you're taking the amount of samples representing a continuous time signal into the discretized time domain, which is you need to balance what's going to be your accuracy requirements, what's going to be your memory requirements as of such. Now for the periodicity property, we know here for continuous time is that once we know what's the periodic time in capital T here, x of t is just going to be the same as x of common t plus capital T. Sorry about that. And then we know for discretized time, if we have x of common in here, we know that after a certain amount of samples being capital n, we can refer this to the period in samples. The signal repeats itself after x of common n plus capital N. We also know for a general sinusoid signal in continuous time, if we have cosine of 2 pi ft plus theta, we know that basically this f here, represented or frequency of the signal, gives us an indication of how the signal itself is represented with respect to our periodic time, capital T, because we know f here is just equal to 1 on t. And no matter what value of f we take, we basically, this is also going to give us a periodic signal, but f here just going to be represented the frequency of the signal as of such. However, when we try to apply this into the discretized time version, this property does not hold true. So it's not going to be periodic for every choice of f, and it's not going to be unique for every choice of f. Accordingly, because remember, in the discretized time version, we're dealing with respect to n being our samples. So, for argument's sake, let's say instead of using common f for continuous frequency, we're going to use capital F here for discretized frequency. And everywhere we had common t is now going to be represented by common n represented all samples. If we try to prove this using our periodic property for x of n that we just saw in the previous slide, and we apply it into this x of n cosine signal as of such, and we expand it out accordingly, we can see here that we'll end up with a capital N and a capital F component as of such. And the only time a discretized time signal in a sinusoid form is going to be periodic is if the combination of capital N and capital F is going to be equal to some integer. We represent this integer here as common k. If the multiplication of these two factors here results in a decimal, that means the periodicity property is broken. So the signal itself in discretized time is not going to be periodic at all. So you need to ensure that when you're dealing with discretized frequency with respect to sinusoids, being in the discretized time domain, that you hold this property here, meaning capital N and capital F is going to be equal to some integer. Or conversely, if you say capital F is just going to be equal to k on n, and you get a rational integer number. Once this property does not give you an integer number, that means the discretized time sinusoid is not going to be periodic whatsoever. So, in analyzing the properties of discretized time sinusoids, we basically see here, and we're going to explain this in the next few slides, is that at omega naught being our centralized frequency, and a phase shift of omega naught plus 2 pi, and you discretized time sinusoid, you're basically going to get the same signal whatsoever. And this brings us to the point as to why discretized time sinusoids are different from continuous time sinusoids. So, for example, if we apply this to a general complex exponent here, being Ej of omega naught plus 2 pi n, and we break this accordingly into its individual components, and we have the omega naught component by itself and the 2 pi component by itself. Because the 2 pi component basically repeats itself, we just go back to Ej of omega naught n. And one thing to note in particular is that this property only exists for generated discrete time sinusoids, not sampled continuous time, not sampled discretized time sinusoids from continuous time signals. So what the property that you're going to observe here in the next few slides, keep in mind this only applies to hardware or software generated discretized time sinusoids, those that are artificially created. They do not apply to discretized time sinusoids from a sampled continuous time signal. So when you actually apply this to a hardware or software generated time sinusoid to observe this property, let's say we started with our centralized frequency here being omega naught equals to 0. So once this is 0 here, we basically just going to get a DC signal, because this means we have no discretized time frequency as of such. Once we do apply some sort of discretized time frequency, we'll get a nice sinusoid as required. However, as we start applying the phase shift here from omega naught to omega naught plus pi, we see that the discretized time frequency is going to be increasing. And as it increases, we're going to use less and less samples to represent our actual discretized time sinusoid itself. Until we reach a point where that we're only going to use like 4 samples here currently to represent the shape of our signal. Because at this point, when we do hit omega naught plus pi, the reason why we need less samples is because we no longer need these intermediary values as of such. It's easier to represent the wave itself just by using these samples here, and you already know the general shape of the signal as of such. Conversely, if we move from omega naught plus pi to a phase shift of omega naught plus 2 pi, as we saw in the previous slides, once we hit omega naught plus 2 pi, we're just going to go back to our original signal being our discretized time sinusoid. So once we start moving from omega naught plus pi, which is going to be our maximum signal frequency, back to omega naught plus 2 pi, that means the signal frequency here in discretized time is going to decrease accordingly. So then we get back to where we're going to require more and more samples to represent our discretized time sinusoid as of such, until we get back to our original signal sample rates as we just now saw from when we had it at omega naught. Conversely, if this omega naught here was a DC value, we'll just go back to our standard DC signal as we saw from the start. So remember, this property that we just saw here in a few slides only applies to hardware or software generated discretized time signals. If you try to apply this property to a discretized time signal that was formed as sampling of a continuous type signal, what you're going to end up is getting an entirely different effect where you actually modify the frequency of the continuous time signal accordingly in discretized time. And as of such, that means you'll actually see the entire graph. If it was a continuous time, it's going to be shrinking and expanding with respect to the frequency that you obtain from continuous time itself. And the reason for this being is that EJ omega naught t in continuous time signals, it's going to be distinct for distinct values of omega naught. But when you move into discretized time, we represent this omega naught here as capital omega, because the common form of the Greek letter here represents continuous time. The capital form here tends to represent discretized time as of such. And the reason why we don't see this expanding and contraction property represented the frequency from continuous time for hardware or software generated discretized time signals is because of that periodicity property that we just observed, is that as of such, the period of n, if we represented this to n capital omega here, needs to be equal to 2 pi k. And remember, that's also going to be representing our integer property that we just saw in the previous slides. So k here needs to be an integer from the property that we just saw in the previous slides. And once k is an integer, that means you don't hold the periodicity property as of such. So because discretized time signals are basically represented as a one-dimensional vector of magnitude values, that means it's a lot easier to manipulate from the continuous time domain. So discretized time signals are way easier to manipulate than continuous time signals in general. So let's observe this with respect to sampling a continuous time signal at 2 different frequency rates to obtain a discretized time signal. So if we take that same 1000 Hz continuous time signal here and we sample it at a rate of 200 Hz, we see here that basically we get a nice representation of our samples here lining up with the signal frequency at the start here as of such. So this here will line up with here, and then we have in between values represented the 200 Hz at which we took the times of those samples, and the endpoint here representing for one period of this 1000 Hz here lines up accordingly where we take our samples accordingly for that periodic time. However, when we sample at 400 Hz, we see here that the samples do not line up with one period of this 1000 Hz continuous time wave. And as of such, that means we're going to be sampling at something referred to as an irregular interval. Because we see here that this sample here now repeats here accordingly, which is like 2 times of the original period of the continuous time wave. So this brings us to an important point when you're actually sampling continuous time waves to produce discretized time sinusoids. Is that such that in order to make sure that you have a proper sampling rate, you need to make sure that when you have the original sequence frequency and you divide it by your sampling frequency, you also get back an integer value. So remember here is that the continuous time frequency was 1000 Hz. And then we had our sampling frequency here for the first instance being 200 Hz. So if we take that 1000 and we divide by 200, we'll get an instance of 5 here, representing the amount of samples so 1 second. Right, this represents the amount of samples that we can actually take for one instance of periodic time from the continuous time signal. Similarly, if we watched for our second sampling rate here, being 400 Hz, we take that 1000 and divide by 400. That comes like if we get 2.5, if my maths is correct. Yes, 2.5. And this maps back here. So how many samples we can take approximately per cycle of that continuous time waveform. And because this is not an integer value, that's why we get something referred to as a regular sampling period as of such when we're trying to get back the original waveform as is. And this also is important because when you do end up getting an integer from this division here, when you reconstruct the wave, you can get back your nice sine wave as of such. But for the 400 Hz sampling, the 400 Hz sampling frequency, we see here that we're not going to get back that nice sine wave if we try to reconstruct it as of such. It's going to be somewhat irregular because of that irregular sampling period as of such. And when we did the division, we got a decimal value. In answering this question here, the least number of samples that is required for any signal being a discretized time signal is typically going to be 4. It's going to be the maximum signal amplitude, the zero crossing, the minimum signal amplitude, and then the next zero crossing. So what this would look like, and if I have space, I can actually show you here. It's going to be like, we just need this sample here, we need this sample, we need this sample here, and we need this sample, and we just keep on repeating. And these here are just going to be 4 samples in particular. So if we try to reconstruct these signals like I just now was explaining, the 200 Hz sampling frequency signal here will give us back a nice accurate representation of our original 1000 Hz continuous time frequency signal. But the 400 Hz sampling frequency signal here is not going to give us a nice reconstruction as of such because of the irregular sampling frequency that we used. So the next few slides are going to show what happens if we try to add and subtract and do some signal manipulation between these two signals as of such. So if we minus those two signals, it comes like if we just minus the magnitude values for each instance of n accordingly. But remember, capital T there, we're going to be ignoring those in particular because the x-axis is with respect to n. So this comes like if we take x of 0 at the 200 Hz frequency and then x of 0 at the 400 Hz frequency, and we just minus those two magnitudes and we get the resultant magnitude, and then we go on to x of 1 and x of 2 and so forth, and we just keep on minusing them accordingly for each magnitude at each n index. And as of such, we get our difference signal here being just a difference of the magnitudes for each instance of n. If we reconstruct this analogly, we see that we get something looking a little bit weird, like if it's a little bit of a sawtooth here as of such, but not a pure sawtooth, but it's going to be like an inverted triangle just right here for each instance. If we compare this to if we did this manipulation in continuous time, we see here that we get somewhat an accurate representation of what the signal may actually look like. But in discretized time, it's just going to be like very sharp edges as of such, because it's an approximation of the continuous time signal. If we multiplied those two discretized time signals for the 200 Hz sampling frequency and the 400 sampling frequency, it's the same concept from when you did the signal difference. Is that we just take x of 0 at 200 and x of 0 at 400 and we just multiply those two magnitudes accordingly. The same thing for x of 1, x of 2 and so forth, and we get our discretized time signal result here as of such. And if we reconstruct this back into the analog domain, we see here that basically we're going to have a series of triangles here with logs in between each instance of the magnitudes. And comparing it with our actual answer, we see here that it's going to be quite different from what we expect. And the reason for this being is that the amount of samples that we took here was limited by the sampling frequency. So as of such, we don't get a nice accurate representation giving us these nice peaks and troughs from continuous time as we see here if we did the manipulation in continuous time. The only way to improve this is that if we up the sampling frequencies accordingly, we may get an accurate representation because there's going to be more samples to represent all these peaks and troughs here, representing changes from continuous time. So the last thing we're going to be discussing in this first lecture is going to be the manipulation of the unit step in particular. And the reason why we use the unit step in particular is it allows us to do a lot more signal analysis and manipulation for any sort of systems that you'll deal with. So if we have a standard unit step sequence here being u of n, if it's starting at -3 here, that means the mathematical notation for this is going to be u of n plus 3 instead. If we flip the unit sequence, such that it's going to be everything 1 on the left hand side before a certain value, and then it's going to be 0 afterwards, this signal here is going to be u of 3 minus n instead. So if we take our one instance. Sorry about that. So if we watch our signal here, being u of n plus 3. I'm going to write it here on the slide. And if we invert it, for this part here, this is going to be minus u n plus 3. Because it's just like if we... Oh, sorry. Nope. My mistake. That's not going to be that. If we watch this signal here, we see here that the change from 0 to 1 is at 0, 1, 2, positive 3. So this here would have been u of n minus 3. And because the signal is inverted, this is going to be minus u of n minus 3. If we take a difference between these two signals here, but in this case it'll just be if we just add the two signals because of this minus here. What happens is that we basically take the magnitudes of each n index here and we just subtract them accordingly as of such. So it comes like this value here for minus 4 and this value here for minus 4. We just basically say, okay, that's going to be 0 minus 0, so we get 0. And then this resultant value here being at minus 3, we can see here for u of n plus 3 minus 3, it's going to be 1. But then for this minus u of n minus 3 here, at minus 3, it's going to be 0. So that's going to be 1 minus 0, only giving us the 1. And similarly, if we keep on doing that for each one of these indexes here, we'll keep on getting the same thing. If we multiply the result here by n, we see here that this n here is going to give us a linear property for our signal, where n represents this nice linear scaling property here as of such. So just to do it for one in particular, let's say for minus 2 here. For minus 2, because we already have the result of u of n plus 3 minus u of n minus 3. Minus 2, 1, 2, that value here was 1. So this entire bracket value here will result to 1, but n here on the outside is going to be minus 2. So as of such, that means that's going to be minus 2 by 1, which is giving us our minus 2 value here accordingly. Similarly, because all these values here were 1, it's not going to be scaled by a factor of n. So it's going to be minus 3, minus 2, minus 1, 0, 1, 2, and so forth. Now, downsampling is a property that can be used when you have too much samples to begin with. And the only time when you try to use downsampling is if you're fairly sure of the signal's behavior. So if you know that signal here is going to be linear in nature, you can just downsample accordingly and use less samples to maximize your memory usage, to minimize your memory usage as of such. So you don't need all these samples here to represent the linear behavior of the signal. You can just use less samples accordingly, and you can choose how many samples you take at what intervals and so forth. And downsampling is similar to the effect like if you have a very huge image and then you shrink it, you still maintain the image quality because you're fairly certain of what the signal behavior is going to be like. Upsampling, on the other hand, it's going to be completely different because that means you're dealing with less information. Now you're trying to get more information, and you don't know what that more information is going to be, so you're going to have to guess as to what you need to fill in for that more information. This is similar to like if you try to take a small image and you try to expand it and make it bigger. You see that the image itself gets very blurred. And that is because we're trying to make an estimated guess as to what the missing information is when you're trying to expand the signal accordingly. So for a particular example here, if we had our original sequence being on linear behavior and we try to expand it, if we're sure that it's going to be linear behavior, we can then approximate those samples in between when we expand it to fit this linear behavior. Typically what happens in simple applications is you just zero fill those samples in between as of such. And that is how you may end up getting something referred to like a blurred effect or an approximate effect, and you don't get back the original signal quality as of such. The only way you can get back the original signal quality is if you're actually sure about the signal behavior and then use a technique referred to as interpolation to fill in those values based on mathematical guesses of the signal behavior itself. So upsampling is when you have the process of less information and you're trying to get more information, but unless you know the signal's behavior to fill in those values accurately, you want to get like a very distorted or a less accurate version of the original signal itself. Alright, so that brings us to the end of our first lecture, which is basically our general recap, where we saw odd sequences and even sequences. We also saw the periodicity property of the hardware and software generated discretized time signals. We also saw how we can do signal manipulation only in the discretized time domain, as well as downsampling and upsampling effects as to how these effects can be adjusted or manipulated accordingly to try to maintain the original signal quality. Are there any questions in particular for the materials of this lecture? Let's see, let's backtrack to slide 23. Oh, it was just intended for visual ease at this point. Just a thing for the signal to be seen more clearly. Yeah, it's just visual ease. I know here that the amplitude here was at 2, but this amplitude here is actually supposed to be 1 on the y-axis. So this here is actually going to be, that's going to be 1, that's going to be 0.5, it's going to be minus 0.5, 1, minus 2, 2. Any further questions? Alright, so that's the end of our first lecture for today. Let's move on to our second recap lecture. That's the second recap. All right, so our second recap lecture here is just going to be reviewing the properties of the unit impulse as to how we can shift it and sift it accordingly and how it can expect a unit step. We also will be observing a few system properties and the impulse response, and then we'll be moving on to convolution as of such. Now, I know some people may have some scary memories of convolution from signals and systems, but I assure you when you actually reach convolution in discretized time, it's a lot easier to actually do this manipulation since we deal with one-dimensional vectors. It's way easier than trying to do those long integral equations that we saw in continuous time. So when we reach there in this lecture and we actually start doing the walkthrough for those problems, you actually see how easier it is to do because of those discretized time signals as of such. So the unit impulse in discretized time is represented by common delta of n, and it's the same sort of visual property that you may observe for the continuous time unit impulse, where it's going to be 0 for everything else other than n equals 0, but at n equals 0, the value here is just going to be 1. And similarly, you can shift it and advance and delay it accordingly. So if it starts at positive 3, that's going to be delta of n minus 3. If it was starting at negative 3, it's going to be delta of n plus 3 and as such. So the unit impulse, if you can actually remember some of the mathematical initiations for it, it's actually the difference of the unit step, where you just take two successive unit step samples, meaning that n here and then n minus 1, you just minus 2, you'll get back the unit impulse accordingly as of such. Similarly, the unit step, being u of n, is just basically a summation of unit impulses, where the index of unit impulses just keeps on shifting accordingly because of that delay and advance property. In order to make sure that this converses to our unit step, remember the unit step here, when it was mathematically defined, get my pen here, so u of n here was basically 0 for n less than 0, and then 1 for n being more than equal to 1. Sorry, more than equal to 0. So this summation series here goes from negative infinity to positive infinity. So to correct this, is going to be u of n here needs to go from positive infinity here, m equals to 0 of delta of m. To make sure that actually matches back to our actual unit step in discretized time. Because for everything else, it's just going to be 0, as we just now saw here from our mathematical notation of the unit step in discretized time. So the sifting property allows us to extract out values by multiplying a unit impulse at that particular n index or that particular time index if we were dealing with continuous time. But because we're dealing with discretized time, we'll be doing it with respect to the sample index being n. So that's like if we say we have some arbitrary discretized time signal here being x of n, and then we multiply it by delta of n being our unit impulse. Because the shift here is just going to be 0, we're going to end up with a result of x naught as of such. Similarly, if we take that same x of n discretized time signal and then we multiply it by delta of n minus k, where it's just going to be a shifted or delayed unit impulse, that allows us to extract out the value of x of n at the instance of k instead. So the multiplication of these two signals will result in x of k. And this shifting of the unit impulse here being multiplied by x of n is what we refer to actually the sifting property of impulses. And it is possible to build any sequence using the same sifting property as of such. If we change the word in here from sequence to samples, and to signals, this entire system property here, when we build in our sequences, is what we refer to as our sampling property when we apply it to continuous time signals. So we use this same system property of the unit impulse here to extract out samples from the continuous time signal and represent it into our discretized time signal domain. So this is like if we have our x of n signal here visually, and we want to similarly extract out each one of these values here accordingly. So we basically say, okay, we want the signal value here at -2 being our n index because our x-axis is in respect to n. So this is going to be of x of -2 here, multiplied by delta of n plus 2, which is going to represent our unit impulse here being shifted to the left by 2 values. So we are able to extract out the value here at -2. Similarly, from -1, it's going to be the same effect. At 0, it's going to be the same thing. At 1 and at 2, we basically just manipulate the equation as such. And then if we want to reconstruct the entire signal here, we just basically represent this as a summation series of each one of these extracted values, where we say it's going to be x of k multiplied by delta of n minus k as of such. We can manipulate the limits here of the summation series to say, okay, which values do we want to extract? So let's say, for instance, we wanted to extract out the values from -2 to 0 here, so -2, -1, and 0. We can rewrite this summation series here, such that it's going to be x of n is going to go from 0 to k equals -2 of x of n, and I'm running out of space here, multiplied by delta of n minus k. See if I can write this a lot more neater. Right, there we go. So that summation series here, we could just manipulate the limits of the summation, allows us to extract out which values in particular we want in a serial sequence. So that will allow us here to extract out -2, -1, and 0 because of the limits of the summation series. If we wanted to extract out, let's say, -2, 0, and then 2, and so forth, we're going to have to do those independently of each other. That's going to come like if we take x of -2 delta of n plus 2, and then we add x of 0 delta of n, and then we add x of 2 delta of n minus 2 accordingly to get those values. And this equation here should look somewhat familiar to you guys if you can actually remember what it's supposed to be. So this equation here basically forms the basis of convolution, and this is similar to the continuous time representation of the convolution series, but because we do in discretized time, we no longer have an integral form, we just have a summation series, and it's just going to be the same thing of x of k delta of n minus k, where it's going to be x of t h of n minus t, if I remember correctly, or something of similar, but it's basically the same form that we can represent from continuous time to discretized time. So the mathematical notations of the unit step function and the impulse function are seen here. Basically, for the unit step, everything n less than 0 is going to be 0. Everything for n more than or equal to 0 is going to be 1. And the impulse is going to be existent only at n equals 0 for 1, and for all other values of n it's just going to be 0. Integration and differentiation in the discretized time domain, it's a lot easier to actually do instead of having to apply these long differentials and integrals. And integration is just going to be a summation series between two limits to represent your limits of your integration of the unit impulse. And similarly, a differential is just going to be the difference between two unit step values as of such. So remember, if you integrate the unit impulse here, you'll get the unit step. And if you differentiate the unit step, you want to get back the unit impulse as of such. So integration and differentiation, it's a lot simpler to do in discretized time. And integration is just going to be a summation of each sample value accordingly. And a differentiation is just going to be the difference between two successive sample points, regardless of where these sample points go. And differentiation is going to be the difference between two successive sample points, meaning that the sample points are right next to each other. That's the correct thing to say. The periodic signals that we just now saw in the previous lecture, for continuous time it's going to be T plus capital T, for continuous time it's going to be N plus capital N. And then if we actually apply these properties for integration and differentiation from continuous time to discretized time, we basically see here that all the integrals that we had in continuous time now just become summation series in discretized time. And everything that was x of t just becomes x of n. Similarly, if we had a limit being applied here, it's just going to be, instead of t tends towards infinity, it's going to be n tends towards infinity. Everything that was t here now becomes n. The summation series represents our integral with our limits being from capital N to minus n. And x of t here just becomes x of n. So we can just straightforward apply these integral and differential properties as is from converting a continuous time equation into discretized time as of such. And we'll be using this finite power signals series that we just saw here when we start doing spectral analysis later on. And like I said from before, because we deal with discretized time signals, it's a lot easier to actually do this mathematical manipulation, to actually do this spectrum analysis. So for any discretized time system, it operates the same way like a continuous time system. You're going to have an input sequence and you're going to produce an output sequence doing some sort of processing on it. But in discretized time, there are several different ways you can actually do this processing. So you can do the processing sample by sample, where you take each instance of each sample and you process it one by one to produce your output sequence as of such. So that comes like if we say x0 by h gives us y0, then x1 by h will give us y1, x2 by h will give us y2, and so forth. This is referred to as sample by sample processing or serial processing, because these samples need to line up and come in one by one in a serial fashion. Typically, when you're dealing with serial data, this is representative of real-time systems where the data is coming in one by one, packet by packet, and so forth. And you need to process each packet accordingly to produce the required output packet. So real-time systems uses sample by sample processing in particular. The other method that you can use, and typically this is used when you actually have data that is stored and is not coming in real time, is what we refer to as block processing or parallel processing. So instead of having the data coming in sequentially, you now have the data represented in a parallel form, and you can actually apply an H matrix here to do the operations to get all the data processed in one go. And block processing or parallel processing is dependent on the type of DSP application that you're using it for. But typically it works for where you actually have all the data already stored and it's just one general operation that you need to perform on all the data as such. The linearity property is basically if we have an f of x signal here, and each instance of the signals here being x1 and x2, x3, and so forth is multiplied by some scalar quantities a1, a2, and a3. we can move up those scalar quantities accordingly for each instant. Excuse me again. Alright, sorry about that. Right. So each scalar instance of x1, x2, and x3 and so forth, we can just shift those scalar properties a1, a2, and a3 to the outside of these f of x1 and f of x2 signals and so forth. But the time invariance property basically just say that if we have y of n equals to some f of x of n, and we do a time shift, sorry, a sample shift with n minus k, that sample shift should be reflected accurately by f of x n minus k. Get back y of n here equal to y of n minus k. And the reason for this is that time invariance means that the input and output, the relationship between the two, does not change with time. At discretized time, it's going to be the relationship between input and output does not change with respect to the sample index. The third property, being causality, is that the system exists for n more than or equal to 0, and for n less than 0, the system does not exist. This is similar to like if the system is being switched on. And causality is mostly exhibited for real-time systems. Okay, guys, I will be right back. I have one thing to attend to, so we'll take a short 5-minute break, and I'll come back in 5 minutes. Alright, okay, so I'm back here. Hopefully I don't get interrupted again. Alright, so continuing where we left off. The discretized time signal is basically going to be made up by a series of weighted inputs, weighted unit samples with the appropriate delays, which gives us back to our convolution sum being our summation series of x of k of delta of n minus k. And remember, because we're dealing with this being a causal signal, that means the signal doesn't exist before n equals 0. We'll be discussing this convolution sum in particular when we reach to our sampler lecture into a little more detail as of such. But for now, we're going to actually just watch how it can be applied accordingly. The linear time invariant characteristic is basically just how do we characterize a signal by the impulse response. And each input x of n, if we manipulate this accordingly and represent it in our convolution sum, we can see here that delta of n minus k, instead of this representation, we can say now that's going to be h of n minus k. So anything that was now delta of n minus k is just going to be wrapped as h n minus k accordingly, due to this linear time invariant property. So instead of writing our x of n as being the summation series of x of k delta n minus k, linear time invariant systems basically represent how do our signals are manipulated by some sort of system being h of n. So that means we'll have our x of k signal here being our input signal, but our h of n signal here being our system that x of k here is going to be manipulated by accordingly. So modifying the convolution sum here to represent our x of k signal here being manipulated by our h of n system, it operates the same way as if it's going to be delta of n minus k. So we just substitute delta of n minus k with h of n minus k. And to get our output system, being y of n, it's just going to be the same convolution sum here, but instead of having delta of n minus k, we now represent our system that's doing the manipulation by h of n minus k instead. Alternatively, that's like if we do a double summation series as well, but we'll be using the simple single summation series here in the yellow shaded block. This manipulation that we see here for a linear time invariant system being h of n that we just saw, it's also expressed as y of n being x of n star h of n. And this yellow block here represents our convolution sum. So in the next few slides, as we reach to it in this lecture, we're going to see how do we apply the convolution sum, our x of n signal, our h of n system, to produce our required output y of n signal. One thing to note is that the order of the convolution, it doesn't matter how do you convolve the signals. You can go x of n star h of n, or you can go h of n star x of n. You will get the same output result regardless. Now, in doing convolution in the discretized time domain, it is possible that if you have an h of n system that does not converge, meaning that it keeps on going towards infinity, the output result of the h of n will be what we refer to as an infinite impulse response system, or IIR. If the h of n system does end at some finite value, or some finite sample index, it is referred to as a finite impulse response system, or FIR. And we'll be discussing IIR and FIR in particular when we hit filter design later on in the lecture series. So for now, let's assume a causal sequence, be a y of n here represented by a convolution sum. If we wanted y of naught, that comes like we have x of k, h of naught minus k. But what's going to be h of minus k? That's simply if we just take h of k and we just reverse it accordingly to get h of minus k. So if we apply the summation series here for y of naught, we'll get x naught, h naught, x1, h of minus 1, and so forth. If we do the same thing for y of 1, if it's 1 minus k, that's going to be the same h of minus k that is flipped, but because the index here is minus k, that positive value of 1 means that the h of minus k is going to be shifted to the right by 1 value. And this 1 minus k just represents a slide. So if we expand this up, we'll get y of 1 here being x naught, h of 1 minus naught, x1, h of 1 minus 1, and so forth. And we keep on going. And eventually we could evaluate for y2, y3, and y4, and so forth. Which is going to be a very long way to try and evaluate it. So let's watch how we can apply this instead to some actual signals and how we can actually perform the convolution sum using these two signals. So we will have our x of n signal here being 1, 3, and 4. Each of n signal here being 5, 4, and 2. Remember, these are discretized time signals, so they're just going to be a one-dimensional vector of values. And we're required to find the convolution of the two, being y of n. Now, remember that the convolution sum that we just saw here was x of k and h of n minus k. And because it's being h of n minus k, this means that the h of n signal was originally flipped or reversed accordingly. So we have our x of n signal here being 1, 3, and 4, which we represent here being 1, 3, and 4. Our h of n signal, because it's going to be h of n minus k, is going to be flipped accordingly. So instead of being 5, 4, and 2, it's now going to be 2, 4, and 5. Because we need to represent this minus k as of such. Remember, convolution operates like if we hold the x of k signal here constant, and the h of n minus k is going to be our sliding signal. So we're going to observe the sliding effect here as we evaluate the convolution. For where we have our first instance of overlap, for these values, it comes like we just only evaluate the multiplication of the two magnitudes for wherever the overlap occurs. So if we watch back our y of naught equation that we just evaluated, that was x naught, h naught, x1, h minus 1, x2, h minus 2, and so forth. H of minus 1 here, you can see is 4. And then x of 1 here is all the way by 3, but there's no overlap, so we can't multiply those two values accordingly. So we only can multiply the values where the overlap actually occurs. So y naught here is just going to be 1 multiplied by 5, which will just give us 5. If we shift the h of n minus k signal by 1, so instead of being h minus k, it's not going to be h of 1 minus k. It comes like we take that 2, 4, 5 that existed here, we just shift it to the right by 1, so it's not going to be 2, 4, 5 here. And if we evaluate the overlap zone here, it's just going to be the evaluation for y of 1 if we watch back our equations that we just now formulated. And where the overlap occurred, this is going to be, for 0, it's going to be 1 multiplied by 4. And then for 1 here, it's going to be 3 multiplied by 5. And we just add the two multiplications together to get our end result. So y of 1 here is going to be 1 multiplied by 4, which gives a value of 4. Add 3 multiplied by 5 here, which is going to be a 15. So that's 15 plus 4, which gives us 19 accordingly. And we can keep on shifting that h of n minus k signal accordingly to for each overlap. And we can keep on calculating it accordingly for y2, y3, y4, and y5, and so forth. So for y2 here, because the signal basically overlaps entirely, it's going to be 1 multiplied by 2 plus 3 multiplied by 4 plus 4 multiplied by 5, and the result is going to be 34. And we can keep on sliding that h of minus k signal throughout the entire thing until we have no overlaps. Because the overlap ends here, there's no longer any overlap for h of k here, and sorry, for x of k here, and h of n minus k here. So at that point, the convolution stops because there's no more overlap. And the end result we're just going to be, give us a y of n vector here in 5, 19, 34, 22, and 8. So this was one of the earlier ways on how to perform discretized time convolution, but then people started realizing as the sequences grew, to try and do this sort of convolution, it's going to just take up a lot of lines of working, and it wasn't very effective actually doing the convolution in this form. So another approach was made such that it could have been a more effective way to actually perform discretized time convolution. And this method was formed by actually analyzing each one of these values here in a simplified form. So we had y0, the y1, the y2 going on all the way to y5 as of such. And we realized that we were dealing with causal systems. And when we just saw those overlaps in the previous slides, because we're dealing with causal systems, that means h of -1 and h of -2, because those are negative indexes, those are just going to be 0. So all these values here that had negative indexes, they just disappear because that's going to be multiplied by 0. So as of such, y of 0 will just mean x0, h0, y of 1 will be x0, h1, and x1, h0, and y of 2 will mean x0, h2, x1, h1, x2, h0. But a pattern started to emerge accordingly. And they realized from this pattern it's possible to form something referred to as the convolution table, which would mean a more way effective way to actually perform discretized time convolution. So they realized that they could have taken all the x values here and listed on the top of the table, and all the h values here and listed on the left hand side of the table. I just need to find the product of each one of these values represented by the cells. So this cell here would have been x0 by h0, and this cell here would have been h0 by x4, and so forth. And they realized, okay, because we've gotten all the values here in the convolution table as of such. So let's actually enter the values here from a previous example, because we had x of n here being 1, 3, 4. And let's backtrack a little bit to see what our h of n was. H of n was 5, 4, 2. H of n was 5, 4, 2. Now one thing to note here is that these values here are h of n. And as we saw just now in the previous slides when we did the sliding effect, we had h of minus n or h of minus k accordingly. So when you're actually doing the convolution table here, there's no need to flip the h of n vector. You can actually use it as is in the convolution table. So because we're using the convolution table going forward, remember this. Do not flip the h of n vector. You are using the h of n vector as is for the convolution table. Okay. So, writing this here. Make sure you do not flip h of n for the convolution table. That is one typical mistakes that some people actually unfortunately do when they're actually doing the convolution using the convolution table. So, alright, so hold on. I need to go back because my ink is blocking some of the annotations at this point. Right. So after doing the multiplications of each one of these cells, in order to get the y of n, you realize that they just need to sum the values across the anti-diagonals from the pattern that they just saw emerging in the previous slides. So y of naught here, if we sum across the anti-diagonal, you'll see that it will give us 5. Y1 here would have been 4 plus 15, which is the same thing that we saw when we did the manual calculations, which gave us a value of 19. And then y2 here would have been 2 plus 12 plus 20, which is given us the value of 22. Y3 here would have been 16 plus 6, which is given us, y2, was 2 plus 12 plus 20, which is given us a value of 34. Y3 would have been 6 plus 16 here, which gives us a value of 22, and y4 here would give us 8. And this would just give us the same output sequence that we just saw when we did the manual form of the convolution. 5, 19, 34, 22, and 8. Okay, 5, 19, 34, 22, and 8. So, moving forward, when you're doing any sort of convolutions, you will be using the convolution table. That means when you have the h of n and the x of n vectors, you use them as is. So remember, do not flip h of n. You're using them as is for the convolution table. So you formulate the convolution table by putting either the x of n values on top or the h of n values, because the order of the convolution does not matter. You can decide where you want to put each one. So for our example here, we put our x of n values on top of the table and our h of n values on the left hand side of the table. And then wherever the cells intersect accordingly, we just did the multiplication. So we got 1 by 5 here will give us 5, 3 by 5 will give us 15, and so forth. And we filled out the table accordingly. And then get the output result, we just summed across the anti-diagonals to get our y of n vector, representing the result of the convolution. So y0 here would have been 5, y1 here would have been 4 plus 15, y2 would have been 2 plus 12 plus 20, y3 would have been 6 plus 16, and y4 here would have been 8. And visually, if we actually plot this, we have seen here, this would be our x of n signal. Oh, sorry, this is the same thing. Visually, if we try to plot this, if we had an x of n sequence here, and a y of n, and an h of n sequence, and we convolved it, we just basically get a nice stem plot here accordingly. Yes, this is the same values, yes. 1, 3, 4, 5, 4, 2, and we convolve those, we got 5, 19, 34, 22, and 6. So let's actually watch an actual practical example here, which we can do for our exam, let's actually do a practical example here, which is something that may actually come on your midterm accordingly. So we can actually see how you can actually apply these questions throughout your midterm and how we can actually evaluate it. So typically you'll be given an input signal x of nt and an output signal h of nt, and you'll be given the value of t here and the index of n going from 0 to 3. So step 1 here is actually to find the sequences h of nt and x of nt before we can begin. So h of nt here being n multiplied by t, that means that t here being 0.1 seconds, and then we'll have t.1 equal by n equals 0, then multiply by n equals 1, n equals 2, and n equals 3. And similarly for x of nt being the exponent of e to the minus nt, we do the same thing. T here being constant, we substitute that as a 0.1, and then we substitute the vector of n being 0, 1, 2, and 3. So you obtain our vector of values here for h of nt and for x of nt accordingly. We then formulate the convolution table by putting the x of nt values here on the top of the table. So we have 1, 0.9, 0.8, and 0.7 here. And our h of nt values here being on the left hand side of the table being 0, 0.1, 0.2, and 0.3 accordingly. We then multiply each of the intersection of values here to formulate the values for each one of these cells. So if we multiply them out accordingly, this row here being 0, it's going to be 0 by 1, that's give us 0, 0 by this value is 0, 0 by this value will just give us 0, and so forth. Then we have 0.1, so that's 0.1 by 1, give us 0.1, 0.1 by this value, 0.1 by this value for here, 0.1 by this value for here, and so forth. And we fill out the table accordingly. We then sum across the antidiagonals to get our result for y of nt, or y of n, being the result of our convolution. So we have 0, 0.10, 0.2, 0.09, 0, 0.3, 0.18, 0.080, and so forth, and we keep on going. Until we get our y of nt values here. Now, a good indicator to know how many values y of nt is going to have is that if we observe how many values that we started with x of nt and h of nt. So x of nt here had 4 values, and h of nt here also had 4 values. If you watch the y of nt signal here, which was the result, this has 1, 2, 3, 4, 5, 6, 7 values. So in order to know that if you're on the right track when you're summing across the antidiagonals, the y length here, so let's call this L of y, needs to be L of x plus L of h minus 1. Where L of x and L of h here represents the length of x of nt and h of nt. This here is going to be 4 plus 4 minus 1 is going to give us 7. And this gives us an indication of how many antidiagonals you actually need to sum across the convolution table in order to get the correct representation of y of nt. Thankfully, because we have MATLAB and then there's the freeware version known as Scilab. Going to write that there. So there's also Scilab. And there's MATLAB. If I can just back just to make sure. Oh, I wrote the wrong thing. Yes, I did write it the wrong way. It is known as Scilab. And then there's also another freeware version which we refer to as Octave. Or you can use Octave Online if you don't want to download the entire thing. All of these will execute MATLAB code accordingly, that which we can see here in this slide. And before I end the lecture, I'll show you guys Octave Online in case you don't want to actually download the entire thing. But it's also kind of advantageous if you do download the entire thing and the internet decides to go, because then you actually have the platform to use offline itself. But it's up to you which one you want to use. You can use Scilab, Octave, or MATLAB to execute any of the code in this course itself. So the code here represents how you actually go about conducting the convolution to actually verify your answer. So in this case, we actually set up our n vector here. The line that's missing is our t vector, sorry, our t value, which we had. So we will need t equals to 0.1, and then these lines here, we'll need to factor in t. So like for instance, x of n here, where you got the exp of negative 0.1 by n by t, and so forth. The same thing for y of n, sorry, same thing for h of n. H of n there would need to be 0.1 by n by t. So that's the only corrections you'll need to make if you actually want to apply the convolution, for example. We just basically use these 4 lines here to actually get our end result for convolution. So it's quite helpful because remember, the midterms and the final exams are going to be open book, so you actually have these lines of code here to execute in Scilab, Octave, or MATLAB to actually verify that if you're getting the actual convolution answer. Just remember that in the marking scheme, the answer is going to be worth 1 mark out of the entire marks. Your marks are going to be allocated on heavily on the method that you use to arrive to your answer. So I'm repeating that for emphasis. Your marks for any of these questions are going to be evaluated and applied on the method used. Final answer is only going to be worth 1 mark out of all the marks allocated for that question. So the code here gives you a nice idea of how you can actually evaluate if you're getting towards the right answer. But you still need to go back and do all of these convolution tables and so forth. And you need to show, well, you won't need to show like all the manual calculations there to fill out the table. You just need to show that you actually did the convolution table and you filled out the table and you actually summed across the anti-diagonals to obtain your y of n vector as the result of the convolution. And like I said, you can use Scilab, Octave. If you have access to MATLAB, you can use that, or you can use Octave Online if you don't want to download it. But it's advantageous if you actually do download Octave and you use it offline. It's not as big as MATLAB, so it doesn't consume a lot of space. So either one you can use, whichever one you're more comfortable with. And before the lecture ends, I'll actually show you guys Octave Online and how we can actually apply this code accordingly to get our convolution. Visually, what this looks like is if we have our x of n sequence here and our h of n sequence, we can convolve it and we'll get our output sequence here as of such. And we can see that basically it's the same result that we just now had. Alright. So that brings us to the end of our second lecture. Are there any particular questions before I show you guys the Octave Online part regarding the material of this lecture? we're using YouTube in particular because in case of anyone having any registration issues and so forth, they'll still be able to watch the lectures regardless. Because if there are registration issues, I don't think people are able to access on Blackboard Collaborate. And if they need access to any of the course material and so forth, it's actually right here. It's a lot more confusing when we have people with microphones interjecting to ask questions and so forth. So if you can ask me any questions via text, it's a lot easier for me to actually manage and so forth. Because if there were 5 or 6 of you asking different questions, it's going to get a lot. Confusing at that point if we're doing audio. We'll be starting tutorials in particular either from next week or the week after. I think we can start the first tutorial from next week. Yeah, it's a lot more manageable once all the questions are lined up in the chat, so I can answer them one by one as we go in. And it also allows for people to type in the question and just have it in queue instead of them waiting to ask it, and they might forget what they need to ask. Alright, so it doesn't look like anyone has any questions regarding the material of this lecture, so I'm going to show you guys how do we use Octave Online here to actually do our convolution evaluations. So let me put this up and bring this across here. Zoom this so you guys can actually see what I'm typing. Alright, so let's watch back our signals here for the question that we just had. So we had t equals to 0.1 and n equals to 0 to 3. So we're actually writing this, in particular we'll say t equals to 0.1 here, and then n is equal to 0 to 3 here. And we can check this. So n here will be 0, 1, 2, and 3, and t here was 0.1. Let's backtrack to our signals. X of nt here was equal to e to the minus nt. So let's evaluate this. So we're going to say x here is equal to exponent of minus n by t. Right? And we can see x here gives us our values, and then h here was n by t. So that's going to be n by t. And we can see h here gives us our values as of such. And then y here represents our convolution, we just call conv being the function of x comma h. And we see here that we obtain the convolution of our values here accordingly. If we evaluate that, you can see here that it just gives us the same values that we just now saw from Octave Online. So using the Octave, MATLAB and so forth, it's a nice way for you to evaluate your answers and see if you're on the right track and so forth for any sort of working that we'll be doing throughout the course. All the code is actually provided for you guys. I'll actually do some live sessions where we can do some code just like this to actually evaluate if you're on the right track. So it's very helpful if you're using this to see if you're getting towards the right answer and so forth. And in particular, remember that the mark scheme for these is that the marks are heavily allocated towards the method and approach that you take and all the working that is done. Now, like I said, you don't need to show all the working for each one of these cells. We understand that's just going to be straight on multiplications, but you still need to like draw the anti-diagonals first to see, okay, how do you went about summing them and so forth. And the final answer is actually going to be just worth 1 mark. So for example, if this question was worth 20 marks, this final answer here, y of nt, is just going to be 1 mark after that's 20. The remaining 19 marks will be for you actually obtaining the h of nt and the x of nt sequences from the equations, formulating the convolution table, and drawing the anti-diagonals to show how you went about summing to get to the final answer. So just remember that the marks allocated for this is going to be heavily focused on the method and the approach and the working that you take. The final answer is just going to be worth 1 mark. Alright, so seeing that there aren't any further questions regarding the material of the lecture and so forth, that would be the end of it for today. And if there are any further questions, feel free to leave them down in the comments below, or you can directly email me and I'll respond to you guys accordingly. So next week, the lectures that we're going to be doing in particular, it's going to be the continuous time Fourier transform, which we have to revisit unfortunately, sampling, and then the discrete time Fourier transform in particular. We'll see that how do we move from the continuous time Fourier transform to the discrete time Fourier transform, which is what we're going to be using throughout the entire course. But we're also going to be doing a few more steps after the discrete time Fourier transform. Actually, how do we move towards what we refer to as the fast Fourier transform, which will be the main basis of what we're actually going to be using in the course for any sort of Fourier transforms. Like I said, because it's discretized time, it's a lot easier to do any sort of manipulations because we're just going to be dealing with numerical values in a vector. So don't get scared, it's a lot easier to do, and the methods are way easier to do than the continuous time counterparts. And you will get full walkthroughs and full examples in class and in the tutorials as well, which will prep you more in advance for the midterms and finals. So until then, take care, be safe, and I will see you guys next week. Later.